At the edge of an international border, at the edge of the Pacific, at the edge of innovation, community, education, and discovery, you're listening to At the Edge of It All, a University of San Diego podcast where USD experts speak on topics and stories that impact you and the broader community.
Hello there, I'm Luce Martinez.
And I'm Elena Gomez, and joining us on the podcast today is Maren Mossman. She is a Clare Boothe Luce Assistant Professor of Physics at the University of San Diego. Maren, thanks for joining us.
Thank you. It's great to be here.
You study physics, and particularly quantum physics, quantum mechanics, and so we'll dive into that. It's something
I want to know all about.
Yeah, it's something we're not well versed in, but we're excited to learn about. But before we dive into all that, we'd love to just learn, why physics? How did you get interested in that? Was that something you were always interested in science when you were younger?
We always like the backstory.
Of course. Yeah. I mean, I love telling the backstory, especially to my students, because it can be sometimes something that they realize, wow, I've had similar experiences.
Absolutely.
So when I was a kid, I always loved astronomy. I was fascinated by the stars, and I wanted to be an astronaut. Like, that was, kid stuff. And then when I got older, I watched a lot of scary space movies and realized, wow, it's dangerous in space. Maybe I want to do something else. And so what I ended up deciding is I'll do astronomy. That sounds great. But then I was told, there's no jobs in astronomy, which is not true, by the way. And so then I decided that, I love science. I just want to pursue science. And so there were a couple other things that I was looking into, like marine biology. I was interested in chemistry for a little bit, but then I took physics in high school and I was absolutely hooked. My physics teacher in high school, Mr. Scari, was just like the greatest human being of all time. And so it kind of just got me hooked into physics, and I realized this is what I really want to do.
And so quantum physics is what you study, which, if we break it down, when we chatted with you earlier, it essentially means you're looking at how things work in our world at the smallest microscopic level. But talk to us as a beginner in all of this. What exactly is quantum mechanics? What do you study?
So quantum mechanics is a branch of physics. So there are many, many branches of physics, and quantum mechanics is just one branch of physics. And it is the study of things that are on the very small scale. So things like electrons, photons, which are particles of light, and atoms. So when I talk about quantum physics, I typically I'm talking about things on the atomic scale. So very, very small. And quantum physics is something that allows us to create a model. Like in physics, we're very passionate about creating models of things to describe the way that something behaves and the way that something should behave from what we've seen in experiments. And so we think about the types of things that we see in everyday life. You have a ball rolling down a hill. We can model that very, very easily using classical mechanics. And that's something that students in the first semester of physics learn how to do. However, when you go down to these really, really small scales, you can't use those rules anymore. Those rules don't apply. A new set of rules applies, which is the theory of quantum mechanics. And fundamentally, the theory of quantum mechanics is a description of matter that's very probabilistic, meaning that you can't know for certain what's going to happen during a measurement until after you've measured it. So you can have, this probability that something is going to be here or there, but before you measure it, you have no idea what it's going to be. You can know everything there is to know about the system, but there's no certainty that you will measure what you think you'll measure.
So you live in the uncertain.
Yeah, pretty much. Yeah. So uncertainty is one of those key principles of quantum mechanics, but really it's the probabilistic nature of matter. And that leads to a lot of different things in quantum physics that are very weird to think about. Like, it's something that kind of makes you need to bend your mind a little bit.
Can you give us some examples?
So the idea of superposition is something that comes from quantum mechanics. And when we talk about a quantum system, we talk about it being in a state. Okay, and a quantum state is a mathematical representation of everything that we know about the system, and that allows us to calculate probabilities. Okay, but a quantum system can be in multiple states at once. An electron can be here or there at the same time, essentially, but we don't know because we haven't measured it yet. Okay, so superposition is the idea that things can be in multiple states at the same time. Okay, there's also the idea of entanglement. Okay, and entanglement means that you have two particles, like you can say two particles of light, or you can say two atoms, two electrons, which when they're prepared in an experiment in such a way that if you measure one of them, you know exactly what's happening with the other. Like you know something about the other one without having to measure it. Okay, this is what Einstein called spooky action at a distance, because you can imagine sending two things really, really far away from each other. And you have one scientist on one end of the universe saying, okay, well, I've measured this. I know exactly what's going on over there, without like kind of like faster than light type of information. But the thing is that you would still need to do a confirmation. So you would still have to send the information from the other scientist on the other side of the universe to confirm that that was in fact true.
Is like time travel in this at all?
Not really. Everything you've seen on Ant-Man is very far-fetched and not really what we mean when we talk about the quantum realm. We talk about the quantum realm as being something that's like a way of understanding matter. We talk about like the weird laws that apply and the weird things that happen when we're at these very small scales, but it's nothing like you've seen in the movies.
One of my favorite movies is Interstellar.
That is a great movie.
What do you think about that movie in reality to what you study? Like, how did you see it through your eyes? I'd love to know that.
I mean, that was a beautiful movie. The visuals in that movie were amazing, and they were informed by science, which is something that I really appreciate, and what a lot of scientists really appreciate is having visualizations of just the universe that are kind of what our models really are right now. And when I talk about models, again, I mean just like the way that we understand something. Towards the end of that movie, I started to kind of like, this is a little bit...
You're like side-eyeing it a little bit.
Too far. It went too far. It's a nice idea. Like, you know, it's a nice movie, and it's a very heartwarming movie. But
were there any parts of it that could help people understand what it is that you do or that scientists do?
Not really. I wouldn't say that aspect of the movie was very well
laid out.
I wouldn't say well informed, but
well, we'll watch it for entertainment purposes.
Exactly. We still like to watch it for entertainment purposes, and the visualizations of the black hole and the visualizations of like what's going on there and the time dilation that they talk about in the movie. So all of that is true.
That's the part that is mind bending to me. Is like getting my head wrapped around that kind of stuff. The time lapses and dilation of all that.
Yeah. So that's based on the theory of special relativity, and that is kind of separate from quantum physics.
Right.
Yeah, but they're all great theories, and like I said, physics is very broad with a lot of different ways of understanding things. That's really exciting.
So the work you do is interesting in the sense that you actually cool down atoms to temperatures very close to 0 degrees, and that's so you can kind of understand what you're talking about in a different way, right? By getting the atoms super, super cold.
Yes. Yeah. So when we want to study quantum mechanics, we can approach it in one of two ways. We can approach it on the scale of, we want to study tiny things. Let's study tiny things. And then you need to have super strong microscopes, but it's really hard to control those experiments in a very tunable way. Or you can approach it from temperature. So you can approach it by cooling things down to temperatures very near absolute zero. So when we talk about 0 degrees, when we talk about making things cold, we might think about it's 0 degrees outside. I need to wear a puffy down jacket, and I need to make sure to wear gloves and a hat. But when I'm talking about cold, I'm talking about a completely different level of cold. Because when we talk about temperature, typically we think about Celsius and Fahrenheit and
right.
temperatures recorded in those units.
That's not what you're doing.
That's not what I'm doing. So 0 degrees Celsius, which is the freezing point of water, is actually 273 Kelvin. And Kelvin is the scale that we use in physics to measure temperature. And as we take that temperature down, we get towards temperatures like 0 Kelvin. 0 Kelvin is what we call absolute zero. That's the limit of temperature. It's a fundamental limit. You can get really, really close to it, but you can never get to zero. And so when I talk about getting very near zero, I'm talking about getting very near absolute zero. And so the atoms that I work with are typically on the order of 100 nanokelvin. And nanokelvin is a prefix for like scientific notation. That means 10 to the minus 9. So I'm talking about 100 times 10 to the minus 9 Kelvin, which is 100, and then you move the decimal 9 places to the left. And that's how close we're getting to absolute zero. And
so that down jacket's not going to help you.
That down jacket is not going to help you, but thankfully it's all contained in an ultra high vacuum system in my lab. And really, when we're talking about temperature, we're talking about how fast things are moving. Because we know as we cool things down, things get a little bit slower, they get slower and slower. But then once you get past a certain point, you start to get behavior that's more wavy. It's more probabilistic. Okay, and so that's where we enter that realm of quantum mechanics. And so that's why we get things very cold.
So for people that are listening, how does the work that you do impact everybody? I know that the work that you're doing is helping to create smaller technologies, right? So our phones that we have, MRI machines, computers, all of them use some of the technology that you work on. So tell us how this all matters to people at home.
Absolutely. So quantum physics has had, applications for many years. And a lot of times it has to do with, like you said, technology and making better technologies. So we've seen huge revolutionary technologies come forward because of our understanding of quantum mechanics, and those include things like the laser, which are used everywhere, and you see them in any lab that you're in. You have MRI machines that you might go get an MRI scan at the doctor, but also the development of diodes and transistors, which are the heart of modern computers and your cell phones. And as we start to learn more and more about these types of systems and how we can manufacture things on a smaller and smaller scale, then we're going to be able to make smaller technologies and maybe technologies that have more capabilities because we can fit more of those transistors onto our circuit boards. Today, so those are all technologies that have already been developed.
Right, that have happened, that are here.
Have happened. They've made a huge impact on society. Now, the thing is that quantum physics is, again, it's like this fundamental study of nature. And so we're trying to learn more about systems fundamentally to be able to develop kind of new exotic types of materials that might have capabilities that we don't really understand yet. Quantum physics is also leading the way in creating pathways for ultra-secure communication methods. So this is something called quantum communication.
What does that look like?
I mean, that's it has to do with encryption and encryption codes to be able to, let's say, if you want to send a bank code, over some line, you have it encrypted. But there are methods of breaking encryption. And so quantum physics, because of this superposition principle that I was talking about earlier, allows you to send messages that cannot be broken. The encryption cannot be broken because of the fundamental nature of quantum mechanics. And so that ultra secure communication is something that's actively being worked on in research labs, not mine necessarily, but that's one application of quantum physics that we're going to see more. We also have quantum computation. So creating more powerful computers that use the power of quantum mechanics to be able to do calculations that are a little bit maybe more complicated than what our modern computers can do.
What would that be useful for, if you can give us an application?
Absolutely. There's actually really cool applications for that. So for instance, in drug development and in chemistry, like physical chemistry, a lot of times you're trying to figure out how to arrange proteins in certain ways and how to arrange molecules in certain ways. And quantum computing as an application, it's not like right now,
right.
We're not seeing that because we're still learning about how to do things. But in the future, you can imagine that that's going to help develop drugs and develop different types of chemicals in a way that is kind of more planned. It's not so much experimentally determined, but it's
right.
something that you can say, I want to optimize this. Do the computation to
right.
do that.
So a bit faster, obviously, too.
Faster. And I mean, those systems...
Inaccurate.
Those systems are, like, at the scale that we're looking at, that would be looking at something at an atomic scale. And so that itself is a quantum system. So why don't we do computations of quantum systems with quantum systems? That seems to make a bit more sense than trying to classically model that.
Now, you have also done some work with the International Space Station.
Yes.
Tell us all about this, because like you, I am fascinated by space and everything that has to do with that. So what were you working on there?
Yeah, so I work on a project called the Cold Atom Lab, which is currently on board the International Space Station. So it's going around every 90 minutes. Taken data, and that's actually a user facility for 5 different teams that are kind of working side by side on different projects. So the project that I'm working on for that has been to study groups of atoms of 3, 4, 5 atoms that are bonded together in a very fragile state. So it's like imagining that you have 3 atoms that are very far apart to each other that are bonded together. You know, we think about molecular bonds, you know, 2 atoms being bound together, and that's a fairly, like, we understand that pretty well. But few body physics, which is the study of 3, 4, 5 atoms being bound together, is a very difficult thing to do. And it's a very difficult thing to sometimes experiment with. And so we have a method for doing that with cold atoms. And so what we're doing is we're trying to figure out how these bonds form and break so that we can better understand things fundamentally in biology and chemistry.
And you've been doing that since you were a grad student.
Absolutely. Yeah. I started that project when I was just a small graduate student, before I had my kids. And so that was in 2014, and I worked on that project all through graduate school. I did my master's thesis on it, and then I am continuing to work on it now.
So for those of us who are not in the sciences, can you explain to us how it feels to have basically another child? You have had this project with you for a major part of your life, and it continues. What is that like for you?
I mean, it makes me sad sometimes because I know at some point it's going to end. You know, I'm trying to enjoy it while it's here and try to get as much out of it as I can. But eventually, you know, it will end like most projects do. And you know, I'm going to have, what I'm going to have left is, you know, the memories, the things, like I got to go see a launch, which was really cool. Like, it was a really amazing experience to go and be really close to a launch site when it was happening. And I mean, obviously the things that we learned from it, and, you know, the lessons learned about doing science and microgravity. It's actually really difficult because when we have our labs on the ground, like the lab that I have is just, you know, down the street in Shiley, and if something breaks, I can just go in and fix it. That's something that, you know, we do a lot in our labs is, you know, if it's physics, it's broken. But on the International Space Station, if something breaks, well, you need to have lots of ways to go around it, or you need to have a plan in place to replace something, or you need to have thought ahead to send up a replacement part that the astronauts can then switch out. And so it's one of those things that it's a very different way of doing science. That's a very weird thing for people like me who do atomic physics. We've never done this before, where we go to, like, we do science on a user facility. It's always, this is our lab. It's built for a very specific thing. But having something that you have to share with other people is also weird. You have to share time and things like that. And it's a different experience.
One last question in terms of this International Space Station project, but like, as you have grown over the years, I'm wondering, like, if you see this project in a different way than when you started, when you were a grad student, and you know, you have different life experiences now, you've been in different places, you've done different things. Like, how has the project and your input in it have grown over time as well?
I think that in terms of the things that I've kind of come to realize is how impressive it all is. Putting an apparatus that fills up my lab over in Shiley, but fits into a very small space and can be completely remote controlled. And it was launched into space, so everything had to be tied down like really tight, and it had to survive vibration tests and everything. You know, just as I've learned more, as I've gotten older, as I've gone through graduate school and then started as a faculty member and started to build up a machine like this myself, it baffles me how they were able to do it. Like how they were able to put everything together and have something that worked. Like that itself is amazing and fascinating. And the fact that it was launched in 2018 and we're still doing research, you know, it was just recently that they replaced the laser systems. Like the fact that they lasted much longer than they thought they would, and they learned a lot just from the first module that they sent up is really great. And it really is a feat of engineering and just control and physics. It's amazing.
And before we wrap up, we also want to talk about something else you're passionate about. You're involved in creating a more inclusive space in physics for everyone. You created a program called the Physics Identity Program at the University of San Diego, which is geared towards women and underrepresented students to help them see themselves as scientists. Students apply, they're paired with a mentor, there's other opportunities to go to conferences for free. Tell us why you started this and why is this important for you?
So I've always been really interested in creating communities in the places that I work. And part of this is because my experience at Washington State University in their Department of Physics and Astronomy was a very welcoming, inclusive, and community-driven space. And so when I came here, you know, we already have a really great community, but I came here in fall 2020, which I'm sure we all remember was a very difficult time for people in academia, in just teaching roles and everything. And so we really wanted to make sure that when people started to come back, that they felt that there was a space for them and that they would have the opportunity to see themselves as a physicist, to see themselves as a biophysicist, and to have a sense of belonging in our department and in the wider community. And so I built the Physics Identity Program as a part of my professorship. As you mentioned, I'm the Clare Boothe Luce professor. And that comes with additional responsibilities having to do with building programming that will retain women, like especially women for that program, but I include everyone for that, that will help retain people in physics, people in my field. And so after doing some research, I realized that growing a physics identity is one of the biggest things that can help retain students. And part of that is because when we have challenges in our careers and in our pathways through getting our degree, a lot of times it's really easy to say, you know what, this is too much. Like, I don't really see myself in this position anyway. I'm going to go do something else. Right. But when you see yourself as belonging, when you see yourself as being a physicist, as a scientist, when you run up into those challenges, it's a lot easier to say, you know what, I can handle that. Like, I can do that. That's something that is just part of who I am now. So that's kind of why I created that, and kind of how I got into that in general. Yeah. Well,
I know that certainly is very valuable, not only to your students, but to so many others, right, who are trying to get into these types of fields that sometimes, as you mentioned, may not be as welcoming feeling for, some.
Yeah.
So thank you for doing that. You're doing incredible things.
Yeah, I'm trying hard.
On Earth and outside of Earth.
There you go. There you go. Universal. Yep.
Yeah. Well, thank you so much for joining us. And if you like this episode, be sure to subscribe to catch our next one.